I have a question for you. There we go. I've got a question for you, and I think it's going to come up in a sheet that I'm going to give you a little bit later. But if we had a compound HOF, now this is a crazy compound, okay? This is like a totally insane compound. I just want you to just be aware that this is going to be whoa, okay? But I want you to try and figure out what the oxidation numbers of H, O, and F are. And I'm going to give you a minute, and I want you to just chat with your partner, chat with your friend, chat with somebody behind you or whatever, and just try and figure this out. And then I'll give you a hint after about 30 or 40 seconds. So go ahead and try this. Yeah. If you weren't here yesterday, the notes package is just back here. Right? 13.3a. Nina, did you get the notes? Okay, thank you. Today, what do you have to do? You have to figure out the oxidation states of all three of these things. Is that okay? Does anybody need a hint? Does anybody want a hint? I would say draw the structure out. That's my hint. There's only three things, and there's no secrets here. It's showing you how they're connected, right? What's the H connected to? The O. What's the O connected to? The H and the F, right? So you know what I mean? So if we draw this out, H, O, F, and we think of our rules, right? Let's think of our rules. What is H normally? +1. What is oxygen normally? -2. So what does that mean fluorine has to be? Does that make sense? Because that doesn't make sense to me. That makes absolutely no sense to me. Nothing about what we learned yesterday shows me that fluorine should be +1. Why should fluorine never be +1? It's got the strongest electronegativity. It pulls harder than any other element. So it can't ever be positive. Fluorine can never, ever, ever, ever be positive, right? And it's like what I told you. This is a crazy example, right? I told you that this was going to be tough and it was going to challenge you. And so, okay, let's go back to basics. Let's go back to the basics and let's try and put the electronegativities. If you're confused, right? So that's 2.2, that's 3.4, and that's 4.0. So let's take a look. Hydrogen and oxygen, who's winning the battle? Oxygen. So hydrogen's +1, and oxygen so far temporarily is -1. Okay? Temporarily. Does that make sense? Now let's go see who's winning the battle between oxygen and fluorine. Fluorine is. So fluorine's going to be -1 and oxygen's going to be +1. So what does that mean oxygen actually is? 0. Does that make sense? That's an insane example. That's a crazy example, okay? But I'm trying to get you to think about where is the fundamentals of oxidation numbers. It shows who does these electrons belong to. They belong to whoever's pulling harder. That's all. Okay? It just so happens that oxygen usually is pulling harder. Anytime you have fluorine in a compound, fluorine can mess some things up every once in a while. Just be careful with fluorine, that's all. Okay? So what I want to do is I want to move on to using oxidation numbers to identify redox reactions. Now, a redox reaction, I got to put all my magnets away. Oh man, here we go. Redox reactions are defined as, well, what's reduction again? Gaining electrons, right? How do you know reduction is gaining electrons? We're not reducing the number of electrons, right? We're reducing the charge. You can think about that. If I said, remember, let's think about this. If I said, I don't know, chlorine went from 0, so Cl2, right? It went from 0 to 2Cl minus. You know what I mean? So it's going from an oxidation state of 0 to an oxidation state of -1. So if this thing, is it gaining or losing electrons? It's getting more negative, so it must be gaining electrons, right? Okay, all right, no problem. I'm just going to draw, I'm going to redraw this here, but I'm going to redraw it on the board. So let's show what happens to its charge. So 0, +1, +2, -1, -2. We start at 0. We start at an oxidation state of 0, and where do we go? -1. Does it make sense now why the term reduction still applies? Because what's happening to the charge? It's getting reduced. Is that okay? So we're still using the term reduction. This thing is getting reduced because its charge is lowering. It's gaining an electron, it's gaining something, but it's being reduced. Is that okay? So reduction is this way, if that's the way you want to think about it. Oxidation is this way. So if something's getting more positive, it's being oxidized. If something's becoming more negative, it's being reduced. That's a different way that you could think about it. Okay, so a redox reaction is an oxidation-reduction reaction. Anytime you have oxidation, you have to have reduction. Does that make sense? If something loses electrons, if electrons leave something, what do you know has to also happen? Something else must have gained electrons. Does that make sense? You can't have electrons just disappearing from nowhere. That would violate the law of conservation of mass. And that would also violate the law of conservation of charge as well. So you can't just have electrons disappear. If something loses electrons, it's because the electrons were transferred from one thing to another. You always have something being oxidized and something being reduced. So we call them redox reactions, because you can identify the thing being oxidized and the thing being reduced. If the oxidation number of an atom or an ion changes during a chemical reaction, then electrons must have been transferred. If this thing is changing from Cl with no charge to Cl minus, it had to have gained electrons. Therefore, this must have been part of a redox reaction. This is half of a redox reaction. So we can identify if oxidation or reduction has occurred based on the change of oxidation state. So if you look at the oxidation state of something at the beginning and the oxidation state of something at the end, and if it changes, you know it must have gained or lost electrons. So we can identify the elements oxidized and reduced in the combustion of coal. Let's try that. Take a look at the combustion of coal. What the hell is coal? Coal is carbon. But that's all it is, just solid carbon. So we'll start with solid carbon, and we're going to combust it. We're going to light it on fire. So what do we have to react carbon with in order to light it on fire? Jaden? Thank you for putting up your hand. Oxygen. Perfect. Now, in a normal combustion reaction, we would get two products. We would get carbon dioxide and what else? Water vapor, right? Can we make water vapor in this case? Why not? Sorry, JC, I just closed that in your face. Why can we not make water vapor? How come I can't put H2O gas here? Why is that wrong and you shouldn't write that down? Why is that terribly, terribly wrong and you should immediately know why? Matthew?
No hydrogen.
There's no hydrogens to start with. So how can we have hydrogens to end with, right? So yeah, you can't make water vapor from this reaction because there's no hydrogens to start with, right? But what can we make? Well, we can make carbon dioxide. So this is the combustion of coal. Coal, for the most part, if it was just pure carbon, we would make pure carbon dioxide or carbon monoxide, maybe. There wasn't enough oxygen. So let's identify the elements that are being oxidized and the elements that are being reduced here in this equation. So let's assign oxidation numbers to every single element in the reactants and the products. So what's the oxidation state of carbon? Are we happy with that? 0? And we understand why? Okay. What about oxygen? 0, right? Because it's an element. Anytime you have an element, the oxidation state has to be 0. What about carbon in carbon dioxide? Okay, maybe we don't immediately know what it is. Then let's identify oxygen. What's oxygen going to be? -2. Oxygen's almost always -2, right? So if the oxygen's -2, then what does the carbon have to be? +4, right? We're happy with that? 2 -2s makes -4, so we have to have +4 here. So let's think about this. Is the carbon gaining or losing electrons? Is it becoming more positive or more negative? More positive, so it must be losing negatives, right? So this is losing. That means what? Is it being oxidized or reduced? If it's losing electron, do you know what the squiggly arrow down means? Did I ever say that? No, I'm representing that as being a loss of electrons. This thing is losing electrons. So that means it's being LEO, right? Loss of electrons is oxidation. So carbon is being oxidized. The thing that's undergoing oxidation is carbon. Now, let's look at oxygen. It's going from 0 to what? -2. So is it gaining or losing electrons? It's gaining electrons. And so that means, right, gaining electrons reduction, this must be reduced. And hopefully that makes sense. If we're starting at 0 and we're going to -2, that's reduction, right? If we're starting at 0 and we're going to +4, that's oxidation. So this doesn't matter which way you want to think about it. Think about it either this way or that way. Whatever, it doesn't matter to me. Can you see how anytime we're getting oxidation, we have to have something else undergoing reduction? It has to happen. if you ever have two squiggly arrows up, something went wrong, right? You're never going to have two squiggly arrows up. Or you're never going to have two squiggly arrows down. Either one up and one down, or one down and one up. That kind of thing. So is this a redox reaction? Yes, it is. Something lost, something gained electrons. Boom, done. Nice. Here we go. Moving on up. Identify if the following reactions. Man, I cannot spell. Holy crap. Following reactions. Our redox reactions. Identify. Okay, that's okay. All right. We'll all get through this together. We're strong and powerful. If they are, identify which substances are being oxidized and which are being reduced. So I want you to take a look at the very first reaction. Take 20 seconds, identify the oxidation states, and tell me which one is being oxidized and which one is being reduced. It's often helpful if in the corner of your page you write Leo and Ger.
Yeah, I'm just wondering, am I late or the word change?
Yeah, we canceled flex
Okay.
for the foreseeable future. That's not your fault.
Okay.
Yeah. Give you 10 seconds to kind of solidify your ideas of what's going on here. Okay, is the zinc gaining or losing electrons? Are we getting more positive or more negative? More positive, and electrons are negative. If you gain an electron, you must get more negative. We're not gaining an electron, we must be losing an electron. So this is being oxidized, right? The hydrogen, what is it, without even thinking about it, what does it have to be?
Plus one.
It has to be reduced. Is it gaining an electron? Yeah, it's going from +1 to 0. It's getting more negative. Yeah, totally, that's being reduced. So all of a sudden, we have zinc being oxidized and hydrogen ions being reduced. No problem. All right, good to go. Methane is burned in the presence of oxygen. Uh-oh. Do you know how to write this reaction?
CH. Something.
Yeah, do you memorize methane?
CH.
Did you memorize methane? It's in here. It's in here. Just look it up. It's in here. Oh, classics. Oh boy, yeah. All right. So if you're burning something, what are you reacting it with?
Oxygen.
Yeah, that's what I'm talking about. Oxygen. When you burn something, when you burn a hydrocarbon, what are you always going to make? Carbon dioxide and water vapor. We should probably balance this reaction just for posterity, right? Because we should always follow the two laws. So, how are you gonna balance this combustion reaction? Where do you want to start?
Carbon.
Carbon, yeah, CHO, right? CHO. You just go in order. So carbon, one carbon, one carbon. Boom. Okay. 4 hydrogens, 4 hydrogens. Then we've got how many oxygens on the right-hand side?
4.
4, right? So we need 2 groups of 2. All right. Perfect. So let's assign some oxidation states. And where do you want to start? What's the easiest oxidation state? You don't have to start at the beginning. You just pick one. What's the easiest oxidation state? Oh, yeah, oxygen, big time. But which oxygen? This oxygen or that oxygen?
No, reactant.
The first one, right? Yeah, big time. 0. That's what I'm talking about. What's the other oxygen? -2, which makes this +1, right? Okay, no problem. This one is also -2, which makes this carbon +4. I know it's hard to see black on black, and that's my fault, but whatever. And then hydrogen is +1, so that makes this carbon what? Ooh, interesting. Okay. So what does the carbon start as? What does the carbon start as? It starts as -4, and what does it end up as? +4. What I want you to think about, is that a tiny change in oxidation state, or is that a big change in oxidation state? That's a massive change in oxidation state. That will usually correspond to lots of energy being either given off or accepted. Does that make sense? Big oxidation state changes usually correspond to big energy changes. And is burning methane a big energy change? Yeah, that's how you heat your home, right? Mostly. Okay, so the carbon, the methane itself, it's the entire thing, not just the carbon, but it's the entire thing that's being oxidized. And then the oxygen is going from 0 to -2. Yeah, the charge is decreasing. So yeah, that's reduced. No problem. So I want to be very explicit. What is being oxidized? What thing should I write here?
Method.
I should write the entire entity. That whole thing. I get it's the C inside the CH4, but the whole thing is being oxidized. And what thing is being reduced? Yeah, it's not just O, it's O2 that's being reduced. So is this a redox reaction? Yeah, redox, right? Yes, absolutely, this is a redox reaction. So go ahead, do the next one, and I purposefully made it about as complicated as I possibly could have. Yes, because I want you to test yourself. I want you to really push yourself and see if you can do this. Now, what's the one thing you probably want to ask yourself? Well, it is balanced, but yes, yeah. But what's, like, let's take a look at the very first compound. What's the one thing you want to ask yourself? Is it ionic or not? Because if it's ionic, you can deal with the ions separately from each other. Does that make sense? Do we have a rule about nitrogen? No. Do we have a rule about sulfur? No. So if you deal with the whole thing together, there's two unknowns. But if you split them up, what's the first ion in here? Come on, Chem 30s. What's the first ion in here? Jaden. Ammonium. Right? Look at ammonium. Do you know the charge on ammonium?
Yeah.
Yeah, then you can figure out that the oxidation state on nitrogen. What's SO4? Sulfate, right? So SO4 has a charge. You can deal with these separately from each other, okay? And then I'm gonna show you a real quick trick at the end. Yeah. Yeah. now we know. Now we don't have to take it out ever. You can wash your hands. So I want to be very clear. You should be working on equation number 3, right? In the notes package. You should not be working on the sheet that I handed out. That's the sheet that I handed out is if you're done that, you go ahead and work on the sheet. But this is way, way, way more important right now. Split up each ion. Yes. Oh, yes. And how many ions are there? 2 of them. Okay, let's look at an NO3 ion. So that means the whole thing is -1. That's that. It's -1. So if you have 3 -2s, if you have 3 -2s, these are the connections. In order for everybody to add up to -1. Right? NO3 ions. Below. So put -2 above the top. Okay, does anybody need some hints?
Yeah.
Anybody need some help? That's okay. We're learning about this. That's all right. So let's think about this. This thing, is it ionic?
Yes.
Yes, it's made out of NH4 plus ions. And separately, right, it's made out of sulfate ions. Would you agree? It just happens to be made out of 2 ammonium ions. But we're just going to deal with one right now because we don't care. Like, one is identical to the other, so just figure out one, okay? So let's think about ammonium itself. Do we have any rules for either nitrogen or hydrogen?
Yeah, hydrogen.
Yeah, we got a rule for hydrogen. Hydrogen is +1. That means, what does the nitrogen have to be if you want it to all add up to be +1? It has to be -3. If it was -4, then the whole thing would add up to be 0, right? Okay, so that's good. Perfect, no problem. Now, let's do sulfate. And do we have any rules for sulfate? Yeah, we get -2 for oxygen. There's 4 oxygens. So what does the sulfur have to be? +6. Okay. Now let's do calcium nitrate. What are the 2 ions in calcium nitrate? Calcium and nitrate. Because this is ionic, let's deal with the ions separately. So we've got calcium, which is 2+. Oop. And we've got nitrate, which is 1-. So obviously this is +2. Okay. What's the oxygen in nitrate? -2. And if there's 3 -2s, that's -6, right? Do we want to cancel out all -6? We want to cancel out 5 of the 6, right? So +5. Okay, are we okay with that so far? So we've assigned oxidation states to everything at the beginning. Let's keep going. Is this an ionic compound?
Yes.
I don't know, is it?
Yes.
Yeah, it is. Why? How do you know?
Ammonia is made of.
Starts with ammonium anything. Ammonium anything. Boom, ionic, right? Ionic compounds begin with metal or ammonium. You should be able to spot it from a mile away. We've been working on this for 3 years now. Okay? So ammonium. Oh, well, what's the oxidation state of nitrogen in ammonium? It's -3. We already figured that out. Okay. So -3 + 1. Do we know what the oxidation states of nitrogen and oxygen are in nitrate?
Yes.
Okay. +5 and -2. Do we know what the oxidation states of calcium and sulfate are? +2, +6, and -2. Do you know where I got these values from? Did the ions change at all? Did the ions change? Did sulfate turn into something that's not sulfate, or did it stay as sulfate? Stayed as sulfate. So did it change? No. Did calcium turn into something that's not calcium? No. Did nitrate turn into something that's not nitrate? If the ions are the exact same at the beginning and at the end, then they can't have gained or lost electrons. Do you see any changes in oxidation states? Do you see any changes in oxidation states anywhere? No, I don't. This is not a redox reaction. There's no oxidation or reduction happening here. It's not a redox reaction. And you could easily do this question in 5 seconds if you know what an ionic compound is. Okay? I'm not trying to bug you. I'm not trying to shame you. I'm trying to show you why it's important you know what an ionic compound is. That's what I'm trying to do. Okay? What do you see at the beginning? What's the first thing you see? Ammonium. Do you see ammonium over here? Yes. Did it change at all? No. Move on. Sulfate. Sulfate. Did it change? No. Move on. Calcium. Calcium. That's a little bit tough, but no, it didn't change. Nitrate. Nitrate. It didn't change. Did any of these ions change? No. double replacement reactions, and this is a double replacement reaction, are often not redox reactions. So this is not a redox reaction. So what I gave you was a sheet. I would like you to work on that sheet, and I would like you to prove to yourself that you are good at the most fundamental tool that you need in your tool belt right now. So there's that oxidation numbers practice. So I would like you to work on this. And at the bottom, it's got, determine the following reactions and see if they're oxidation or reduction reactions. If it is a redox reaction, then tell me what's going on. If it isn't, then whatever, then not. That's fine. B we already did, right? We just did B.
Yeah.
So I mean, it might be the opposite of what we did, but whatever. It's fine. I think it's the exact same thing. It's not that big of a deal. So just go through here and try and figure out what all the oxidation states of all of this garbage is, and then we'll kind of get back together in about 10 or 15 minutes, and we'll go through the answer to what I want to be very, very specific about. If you've got no clue what's going on, if you got no clue at all, what I want you to do is I want you to bring your notes, and I want you to take your notes out into the lab, and you're going to work with me on this. This is such a fundamental process.